You're watching Cosmohypnia for those who still look up. October 29th, 2025. An interstellar visitor, a comet from beyond our solar system, reached the sun, and it should have grown a tail. Every comet does, every single one. When ice gets close to the sun, it heats up, gas escapes, dust gets kicked free, and a brilliant tail stretches millions of kilometers into space, glowing like a ribbon of light. That's what comets do. It's their signature, their calling card. Except this one didn't. When 3I Atlas emerged from behind the sun, the tail was gone. Not faint, not hidden, just gone. Let me be clear about what we're dealing with. This isn't some chunk of rock from the asteroid belt. This is an interstellar object. It came from another star system, another sun, maybe billions of years ago. It's been drifting through the void between stars longer than Earth has existed. Through darkness so complete and so vast that light itself takes years to cross it. And now, for the first and only time in its existence, it's passing through the warmth of our sun. Think about that for a second. This thing has been alone in the cold for longer than we can imagine. And now it's here, briefly, just once. We've only confirmed 3 interstellar visitors before this. The first was Oumuamua in 2017. That strange cigar-shaped rock that tumbled through silently, reflecting sunlight but releasing no gas, no glow, no activity. The second was 2I Borisov in 2019, a comet that looked almost normal. It had a tail, it had dust, it behaved exactly like the comets born in our own solar system. But 3I Atlas is neither. It sits somewhere in between, glowing, active, releasing enormous amounts of gas into space but no dust, no tail. Just this blue ghostly halo surrounding a dark core, stretching outward and then fading into nothing like breath on a cold window. Except this breath is traveling at thousands of kilometers per hour and glowing in wavelengths invisible to the human eye. The Atlas survey in Hawaii spotted it first, months before it reached the sun, and right away astronomers knew something was off. The orbit looked wrong, it was moving too fast and the path was too straight. This wasn't something trapped in our solar system's gravity. This was something passing through, a visitor, not a resident. As it got closer to the sun, things started to get strange. Comets brighten as they approach. That's normal. Heat warms the ice, gas escapes, and the glowing cloud around the nucleus, we call it the coma, grows larger and brighter. But 3I Atlas didn't just brighten. It exploded in brightness. 2 astronomers were watching it closely. Chi-Chang Jiang, working late nights at Lulin Observatory in Taiwan, and Carl Batams at the US Naval Research Laboratory. They both watched the brightness curve, the graph tracking how much light the comet was giving off, and saw something that made no sense. The brightness doubled within days, not gradually, not smoothly. It jumped, like someone had flipped a switch. And here's the number that made them stop and stare. In just 2 weeks, 3I Atlas started releasing water vapor at a rate 40 times higher than it had been a month earlier. 40 times. Imagine 20 Olympic swimming pools worth of water evaporating into space every single day. That's how much material was pouring out of this thing. And yet, no dust appeared. Not in any telescope, not in any image. When a comet gets close to the sun, solar heat doesn't just melt ice, it breaks it free. Dust particles locked inside the ice get released, and sunlight pushes them outward, forming that classic glowing tail we all recognize. But here, nothing. 3 different satellites were watching, SOHO, Stereo, and GOES 19. 3 different angles, 3 different cameras, and all of them saw the same thing, a glowing cloud. Gas-rich, but no tail. NASA's Swift telescope, which sees in ultraviolet light, the kind invisible to our eyes, detected something else. It saw the signature of water vapor being torn apart by sunlight. The chemistry was there, the molecules were there. Everything screamed, this is a comet. But visually, it looked more like a leak, a cloud of gas expanding into the void. Not the fiery, dramatic tail we expect, just mist. Glowing blue and fading into darkness. Think about that. Every measurement confirmed this thing was venting massive amounts of water into space. The chemical fingerprints were clear: water, carbon dioxide, ammonia fragments, all the ingredients of a normal comet. But the image showed no tail, no dust stream, just a smooth, eerie glow. It looked wrong. It looked alien. If you want to keep following stories like this, objects that challenge everything we thought we understood, stay with us and hit subscribe. Because what's unfolding right now with 3I Atlas is just the beginning. Scientists scrambled for explanations. One idea focused on carbon dioxide. CO2, frozen carbon dioxide, turns to gas at lower temperatures than water ice, which means it escapes first, farther from the sun. Some researchers thought maybe this early CO2 gas acted like a protective blanket over the surface, cooling it down and keeping the water ice underneath frozen. But then, as the comet got even closer to the sun, that blanket ran out. It evaporated completely, and when it did, the water ice underneath was suddenly exposed to full direct sunlight. The result was an eruption. Water vapor exploding outward 40 times more than before. But, and here's the key, if that eruption happened fast enough, maybe the gas could escape without dragging solid particles with it. No dust, just pure vapor. It's possible, but it still doesn't fully explain why there's no dust at all. Another group of scientists suggested something more radical. What if the composition of 3I Atlas is just fundamentally different from anything we've ever studied? Remember, this thing didn't form here. It formed around a different star, a completely different environment, with different temperatures and different chemistry. What if its core is almost entirely ice, frozen gas, with barely any rocky material inside? If there's no dust to begin with, then no amount of heating will create a tail. You can't release what isn't there. Here's where things get even stranger. The James Webb Space Telescope, the most powerful infrared telescope ever built, had been watching 3I Atlas for months, and it found something that changes the whole picture. Webb revealed that this comet has been transformed by radiation. Not solar radiation, but cosmic radiation. High-energy particles that race through the galaxy. Fragments of exploded stars, protons traveling at nearly the speed of light. In our solar system, we have some protection from them, because the sun creates a magnetic bubble that deflects most cosmic rays away from us. But out there in interstellar space, there's no shield, nothing to protect you. And 3I Atlas has been drifting through that radiation storm for billions of years. Imagine what that does to ice. Every cosmic ray that hits the surface breaks chemical bonds, changes molecules, and hardens the structure. Over millions of years, the outer layers transform into something new, something denser, darker, and harder. Research led by Roma Maggiolo, an astrophysicist in Belgium, showed that after about 1 billion years of this bombardment, a comet's surface becomes a crust, a shell about 20 meters deep. This crust doesn't behave like normal ice. It traps gas underneath. It resists breaking apart, and when it heats up near the sun, it releases gas but almost no solid debris. If 3I Atlas is covered in this kind of shell, then the missing tail isn't a mystery. It's inevitable. Let that sink in for a moment. Scientists had been hoping that interstellar comets would give us a window into other star systems, a pristine sample from a distant sun. But if Maggiolo is right, what we're looking at isn't a relic from another world. It's a fossil of the journey itself. A surface rewritten by billions of years in the dark, scarred, altered, transformed. Maggiolo said it himself. 3. Atlas is now a product of its journey, not where it came from. Which raises a question. What's underneath that crust? What's hidden in the core that might still carry the original chemistry from its home system? And will we ever see it? Here's something you probably don't know. Avi Loeb, former chair of Harvard's astronomy department and known for asking uncomfortable questions, formally asked NASA to release all the data on 3I Atlas, not just the cleaned up images or summaries, but everything. Raw files, unprocessed frames and observation logs. Why would he do that? What does he think might be hidden in that data? Loeb has always pushed for transparency when it comes to interstellar objects, arguing that these visitors are too rare and too important to keep locked behind institutional walls. But his request also suggests something else, a question left hanging. If there's nothing unusual about this comet, if it's behaving exactly as models predict, then why the delay in releasing the raw images? NASA says the data will come after calibration, which is standard procedure. But in an age of instant uploads and live streams, delays feel like secrets, and secrets breed suspicion. Here's what we know for sure. At its brightest, 3I Atlas was visible through small telescopes if you knew exactly where to look. But there was a problem. It was so close to the sun in our sky that Earth-based observation was nearly impossible. The sun's glare drowned it out. So we had to rely entirely on space-based satellites, machines designed to stare directly at the sun to see what was happening. And what they saw looked nothing like a normal comet. No sweeping tail, no glittering arc of dust, just an elongated glow, gas without reflection. A comet missing the one thing that makes a comet a comet. So where does that leave us? The images are real, the chemistry checks out, but the models don't quite fit. We have an interstellar traveler that drifted for billions of years, survived cosmic radiation, approached the sun, flared with intensity no one predicted, and then moved on. Intact, dustless, silent. It didn't shatter or break apart. It just vented, like opening a valve on a pressure tank and watching the steam escape. And now it's fading back into the dark, carrying questions we're only beginning to know how to ask. By the end of October, the data started behaving strangely. The brightness climbed faster than it should, twice as fast as any model predicted. That's not a small deviation or noise in the instruments. That's the universe telling us we missed something. But here's what made astronomers pause and stare at their screens. The light itself looked wrong. When sunlight hits dust, solid particles, it bounces in a specific way and scatters, creating a measurable pattern. But the light coming from 3I Atlas scattered as if it were hitting mist, not grains, like shining a flashlight through fog instead of sand. That meant one thing. The material escaping the comet wasn't solid. It was gas. Pure invisible gas glowing blue in the vacuum of space. That ruled out instrument error and camera tricks. The tail wasn't faint. It wasn't hidden behind some technical glitch. It simply wasn't there. At this point in the comet's orbit, the geometry was perfect, and any dust, even a thin stream, should have been easy to see, stretching directly toward Earth and lit up by the sun behind it. But the images stayed blank. Only a smooth cyan glow spread across hundreds of thousands of kilometers. Gas gives color, dust gives shape, and here only color remained. Normal comets release dust, even small amounts. Particles just a few thousandths of a millimeter across, smaller than a grain of sand, but still enough to catch sunlight and create that iconic glowing tail. But 3I Atlas released nothing. Instead, instruments picked up chemical signatures, water molecules torn apart by ultraviolet light, glowing at specific wavelengths, and carbon compounds fluorescing under solar radiation. All familiar chemistry, all happening without a single solid particle. It is like watching someone boil water and seeing only steam. No droplets, no mist, just invisible vapor rising into the air, except this steam is traveling faster than a bullet and glowing in colors you cannot see with your eyes. Early images from satellites showed something strange. A narrow plume extended from the nucleus, the solid core of the comet, but it did not last. It appeared, flared, and then faded within minutes. Analysts compared it to bursts of carbon dioxide gas, sudden jets that erupt when frozen carbon dioxide turns directly into vapor and escapes through cracks in the surface. These jets flash, they do not linger, while normal comet tails persist for days or weeks as dust slowly drifts away. This was different, violent, brief, and then gone. Chi Changjiang, watching from Taiwan, wrote one line in his notes: bright, gas, no dust. Carl Batams at the Naval Research Lab added, activity spike, cause unknown. Professional language, measured and careful, but you can feel the confusion between the words. As the days passed, the numbers kept climbing. Water vapor poured out of the comet at a staggering rate, roughly 2,000 tons every hour. Imagine 20 Olympic swimming pools, and then picture all that water evaporating into space every single day. That is how much mass was leaving the nucleus. And still, no dust appeared. No glow, no arc, no tail, just gas invisible to the naked eye, but blazing in ultraviolet and infrared. Some researchers proposed an explanation. Maybe the comet's ice is not like ours. After billions of years drifting through interstellar space, exposed to cosmic radiation, the surface layers could have changed. Volatile gases, things like carbon dioxide and carbon monoxide, might have separated from heavier materials and collected near the top. When solar heat arrived, those gases escaped first and carried nothing with them. No dust, no grains, just vapor expanding into the vacuum. It is not impossible, it is just rare. Others argued that maybe sunlight itself pushed the dust away. Solar radiation creates a gentle pressure, a push that can sweep small particles beyond the range of our cameras. Maybe the dust was there, but we just could not see it. Possible, but the angles did not support it. Even faint dust arcs should have shown up somewhere in the frame, yet the detectors stayed blank. Then something unexpected appeared in the data. A weather satellite, not even designed to watch comets, picked up brief X-ray flashes near the comet's position. Not flares or noise, but subtle bursts of light appearing and fading over minutes. Here is what was happening. The solar wind, a constant stream of charged particles flowing from the sun, was slamming into the comet's gas cloud. When that happens, the gas becomes ionized, electrically charged, and charged gas glows. It is like a miniature aurora, a plasma light show in the emptiness of space. No dust needed, just physics at work. It was one more clue that 3I Atlas was behaving more like a venting gas cloud than a traditional comet. Meanwhile, the James Webb Space Telescope had been watching for months. Back in August, long before the outburst, Webb detected something important, a specific wavelength of light, the signature of frozen carbon dioxide ice covering the surface. But after the flare, that signature weakened and almost disappeared. Here is what that tells us. The thin layer of carbon dioxide on the surface sublimated completely, turning straight from solid to gas. When it did, it exposed the water ice buried underneath, and suddenly that water ice was hit with full direct sunlight. The pressure spiked, water vapor erupted outward in a torrent, and then just as quickly the surface cooled again, forming a smooth glassy shell. The radiation-hardened crust that had been building for billions of years. Dense, brittle, with almost no dust left to release. In effect, the comet had sealed itself. By early November, the brightness started to fade slowly and steadily, about half as bright each day. That is normal when surface ice runs out, but the color stayed the same and the chemistry stayed the same. No new structures appeared. No dust emerged later. The glowing cloud around the nucleus shrank evenly. The comet was calming down, activity without destruction. Rare, but not impossible, and it fit the observations perfectly. Then the conversation shifted. On November 2nd, several independent astronomers made a request. They wanted access to the raw image files from the satellites that had been watching the comet. Not the processed versions or the cleaned-up press images, but the original frames. NASA's response was simple. Data will be released after internal calibration. Standard procedure, nothing unusual. But here is the problem. In the age of instant uploads and real-time streaming, delays feel like secrets. If nothing strange happened, why hold back the images? Why not release them immediately and let the community analyze them? It is not an accusation, it is a question. But questions like that fuel speculation. Avi Loeb, who has never been shy about demanding transparency, spoke up again. He has been calling for open access to interstellar object data for years, and his argument is simple. Transparency prevents conspiracy theories, while delays create them. And he was right. Each day without images added weight to the rumors. People started asking what NASA might be hiding. Was there something in those frames that contradicted the official story? Was there a faint tale that got filtered out? The answer most likely is no. The reality is simpler. Multiple instruments, different teams, same result. Rapid brightening, massive gas output, no dust. The absence was not a mistake, it was the observation. At its brightest, 3I Atlas was visible through backyard telescopes, but its position near the sun made ground observation nearly impossible. We saw it only through machines built to stare directly at the star, and that shaped how people perceived it. The event felt distant, filtered, abstract. Most people never got to see it with their own eyes. It was a comet observed entirely through data streams and processed images, and data, cold, numerical, invisible, does not inspire awe the way a glowing tail in the night sky does. If cosmic rays really did turn the surface into a glassy shell, then a dust tail was never going to happen. The crust would have sealed itself long before solar heat could break anything free. Imagine trying to boil water inside a stone. Pressure builds, steam escapes through cracks, but the walls hold. The comet behaved the same way, venting, not shedding. So what is it? A comet by classification, an asteroid by appearance, a chemical puzzle by behavior. The label 3I Atlas remains, but the word comet does not quite fit anymore. It is like trying to describe a cloud as solid, technically accurate, but it feels wrong. As the flare faded, scientists reached a quiet agreement. The physics worked, the chemistry was strange but not impossible. No new forces, no hidden mysteries, just matter shaped by time and radiation, responding to heat in a way we had not seen before. Strip away the speculation, and here is what you are left with. An ancient nucleus, a thin layer of frozen carbon dioxide, sunlight, pressure, gas escaping into the void, and nothing left to form a tail. That is the anatomy of the anomaly, not a violation of the laws of nature, just an extreme case played out in real time across the face of the sun for anyone watching closely enough to notice. And the question that lingers now is this. If this is what one interstellar comet looks like, how many others have passed through leaving no trace because they looked exactly like this? Invisible, silent, gone before we even knew they were there. Before the flare, before the missing tail became a mystery, the story of 3I Atlas was already written in its surface. Everything about it, the muted color, the strange resilience, the way it responded to heat, pointed to one truth. This object had spent billions of years outside any solar system, alone, under constant bombardment from radiation. Cosmic rays are high-energy particles that cross the galaxy at nearly the speed of light, fragments of exploded stars, protons accelerated by black holes, atomic nuclei stripped of their electrons. They race through the void, unstoppable. And when they hit something like ice, rock, or dust, they do not just bounce off, they change it. Every impact breaks chemical bonds, rearranges molecules, and darkens the surface. Over time, those reactions turn a soft, porous comet crust into something else entirely, something harder, denser, and less reactive. A shell that no longer behaves like the ice it was born from. Roma Maggiolo, an astrophysicist in Belgium, and his team modeled this process in detail. They simulated what happens to ice when it is exposed to cosmic rays for 1 billion years, and the results were striking. The radiation penetrates deep, roughly 20 meters below the surface. It does not just affect the top layer, it rewrites the structure all the way down. What you are left with is a fossilized crust, not the original material, not a snapshot of the comet's birth, but a record of survival and endurance. When 3I Atlas began heating near the sun, that crust reacted like glass under stress. It cracked, vented gas, then resealed. Each cycle released water vapor, carbon dioxide, and ammonia fragments, but kept the shell largely intact. That is why the data looked the way it did, with sudden bursts of brightness, then quiet periods, and almost no dust. The crust was too hard to crumble, too dense to shed particles. It could only vent. In laboratory terms, this process is called amorphization. when crystalline ice loses its structure under radiation. What was once clear becomes opaque. What was once porous becomes solid. Light cannot penetrate deeply anymore. Gas escapes only through fractures, and the comet's behavior near the Sun matched this pattern perfectly. Not speculation, not theory, the chemical fingerprints were right there in the data. Webb's infrared observations showed a broad, smooth spectrum typical of carbon-rich glass, not crystalline ice. The surface had transformed. For years, scientists hoped that interstellar comets would offer something precious, a pristine sample from another star system, untouched material from the disk of gas and dust where planets form, a window into how other worlds are born. But 3I Atlas shattered that hope. If Maggiolo's model is correct, what we are seeing is not an unaltered relic. It is a survivor, a surface rewritten by the journey, scarred by radiation, hardened by time. We are not studying where it came from. We are studying what it became along the way. That shift is subtle but profound. Instead of asking what was its home system like, scientists now ask what happens to matter during millions of years in the dark. Interstellar space is not empty. It is filled with dust, magnetic fields, and high-energy particles acting like slow sandpaper, altering anything that drifts through. Every collision adds new compounds. Every radiation strike darkens the surface. By the time a body like Atlas reaches us, it has already been rewritten by the medium between stars. The data suggests that 3I Atlas is roughly 3 times denser than a typical comet from our solar system. That density means it holds heat longer, cracks less easily, and prevents the release of solid particles. What looks like a compositional mystery might just be mechanical resistance, a surface that can vent gas but refuses to crumble. NASA's official statement called it a rare but natural case of gas-dominant behavior. ESA repeated the same line, technically true, but beneath the careful phrasing lies a deeper realization. The familiar categories of comet, asteroid, and interstellar object are starting to blur. We are seeing variations that fall between definitions, shaped more by time and exposure than by origin. Independent teams from Korea, Chile, and Japan kept tracking the comet after it passed the Sun. They confirmed everything: the blue spectrum, the negative polarization, the stable rotation of about 12 hours per spin. That slow rotation might explain why one side of the nucleus released jets, while the other stayed dormant. Uneven heating, uneven venting. It is another reason dust might never have formed. The surface simply did not grind itself apart. Still, the differences between known interstellar visitors remain striking. Oumuamua showed no activity at all. No coma, no tail, just reflected light. 2I Borisov had an abundant dust tail and broke apart quickly under solar heat. 3I Atlas sits between them, bright, gaseous, but intact. 3 travelers, 3 chemistries, no pattern. The category of interstellar object might be too broad to describe what we are actually seeing. The deeper question is not just about this one comet. It is about process, about how information moves through institutions and how public understanding lags behind discovery. When raw images take months to appear, curiosity fills the gap with speculation. When official statements arrive polished and identical, they sound defensive even when they are factual. It is a communication problem layered on top of a scientific one, but the numbers themselves do not lie. 40 times more water vapor than a month before. No dust in any wavelength. A surface that held its structure under extreme heat and radiation. All consistent with the crust hypothesis. A fragile body would have shattered. This one endured. That endurance is its defining feature. The simplest explanation fits best. An ancient interstellar nucleus, hardened by cosmic rays, flaring once as sunlight cracked its surface, then cooling again into silence. No new physics required. Just the known laws stretched over billions of years. Yet the image stays with people. A comet passing the Sun without the trail that makes comets recognizable. It looked unusual, not because it defied physics, but because it defied visual expectation. In that sense, the discomfort is human, not cosmic. By the end of the first week of November, data from all observatories aligned. The flare was over, brightness declining smoothly, gas emissions continuing but fading, no fragmentation, no dust, no surprises. A single stable object moving outward again. 3i Atlas has become less a mystery and more a test of perception. It is proof that nature can follow its rules perfectly and still look strange to us. The data close the gap between expectation and reality, but the feeling of anomaly remains. And perhaps that is the quiet lesson. The extraordinary is often just the ordinary seen through distance, radiation, and time. We wanted revelation. What we got was endurance, and maybe that is more remarkable. After the flare subsided, the comet entered a quieter phase. Brightness faded slowly, color stayed blue, and still there was no trace of dust. By the first week of November, multiple observatories confirmed the same picture. 3i Atlas remained active but unusually clean. Gas dominated everything. James Webb's infrared observations provided the most detailed chemical portrait. It measured light at wavelengths invisible to the human eye, the kind of light that reveals what molecules are doing, how they are vibrating, and what they are made of. Webb saw carbon dioxide, strong absorption at a specific wavelength, and water vapor with lines appearing where water molecules absorb infrared light. These are standard markers of sublimation, frozen gases turning directly into vapor when exposed to sunlight. But here is what was missing: the familiar peaks around longer wavelengths that indicate dust. Silicate minerals, rocky material, absorb light in a distinctive pattern, and that pattern was not there. Instead, Webb recorded a smooth, flat continuum, gas in motion, not grains reflecting light. That flatness told its own story. Molecules, not minerals. Vapor, not particles. It was confirmation, not contradiction. NASA's Swift telescope filled in the other side of the data. It captured ultraviolet light, the kind that gets absorbed by Earth's atmosphere and is invisible from the ground. Swift saw hydroxyl emission, produced when sunlight tears water molecules apart, and that line remained steady even as overall brightness declined. That meant the comet was still venting water vapor long after the outburst ended. Gas persisted. Solids never appeared. Laboratory comparisons helped interpret those readings. Each frozen compound, carbon dioxide, ammonia, and water, has a unique absorption fingerprint. The ratios in Atlas matched a composition rich in volatiles but depleted in rocky material. That combination is rare. 2i Borisov, the previous interstellar comet, had clear silicate features, signs of dust. Atlas did not. Different chemistry, different origin, possibly formed farther from its parent star, where only ices condensed and rocky grains never coalesced. The blue color shift in visible light came from something called fluorescence, light emitted by excited gas molecules when struck by sunlight. Ammonia fragments and carbon compounds glowing blue. Nothing mysterious, but unusually strong. The intensity exceeded predictions. Some suspected instrument calibration issues, but independent ground-based telescopes catching brief glimpses during twilight confirmed the same trend. The blue stayed, and so did the unease. If the color was not an error, it had to come from physics near the sun, within 1/10 of an astronomical unit. Roughly 10 million kilometers, the solar wind is dense, a stream of charged particles moving hundreds of kilometers per second. When that plasma hits a gas cloud rich in water and carbon, it generates a temporary sheath of ionized gas. That sheath emits additional blue light. In satellite data, minor X-ray variations coincided with the brightest intervals of the comet's glow. The match was not perfect, but close enough to suggest ionization played a role. Each observation reinforced the same point: intense gas activity, persistent emission, no dust. NASA summarized it as volatile-dominated composition. It sounded routine, but it marked a major departure from the norm. Most comets carry roughly equal parts gas and dust. In 3i Atlas, volatiles appear to exceed 90%. That single ratio changes everything. How light reflects, how tails form, how long a nucleus can survive near the sun. The absence of dust also reshaped the question of origin. If comets inherit their composition from their home systems, then a dust-free surface suggests formation in a region poor in rocky material, perhaps far from its parent star where temperatures were so low that only ices condensed. That environment would produce a body made mostly of frozen gases such as carbon dioxide, water, and ammonia, with little to release when heated. Such an object would not crumble. It would vent and move on. By November 7th, measurements from observatories in Chile, Spain, and Hawaii aligned almost exactly. Brightness around magnitude 10, fading steadily. Spectrum showing a blue continuum, strong carbon dioxide, declining water vapor, and no silicates, all pointed toward the same physical interpretation. A nucleus that survived heating intact because its crust was already hardened by radiation and poor in solids. That consistency gave weight to the irradiated traveler hypothesis. Cosmic rays had compacted the outer layers, sealing dust beneath or destroying it outright. When heat arrived, gas escaped through microfractures, but solids stayed locked in place. The physics did not break. It simply ran out of available dust to carry. Still, not everyone was convinced the story was complete. Some scientists wanted access to raw coronagraph frames to rule out faint dust arcs hidden by image processing. NASA and ESA responded that internal calibration was still underway, a reasonable explanation. But in a digital age, delays feel like secrecy. Avi Loeb renewed his call for immediate data release, arguing that openness prevents conspiracy faster than press releases do. He was not alone. Several independent teams echoed the sentiment. Transparency first, analysis later. That debate had little effect on the science itself. The data that were public already agreed across all instruments. SOHO, stereo, Swift, and Webb. Different wavelengths, same conclusion. Gas dominated, dust absent. Each telescope spoke a different technical language, but told the same story. For the researchers, that convergence was enough. The event was still ongoing, but its behavior was consistent. No new flares, no breakup, no dust emerging as it moved away from the sun. It was behaving predictably in an unpredictable category. For the public, predictability felt anticlimactic. After the initial headlines, the silence of confirmation seemed suspicious. People asked why images were missing, why agencies spoke in identical phrasing, why nothing new was happening. The answer was simple. Nothing was supposed to happen. The object had stabilized. The science continued quietly. The spectrum itself, those thousands of lines of data, is what remains. Every wavelength corresponds to a molecule, every ratio to a physical condition. Together they outline a picture that is neither sensational nor trivial. A comet made of ordinary elements shaped by extraordinary time. A chemical balance inherited from another star, preserved through radiation, revealed by sunlight. By the first week of November, the pattern was settled. Gas where dust should be. Light without reflection. A steady decline in brightness as the comet receded from the sun. No tail, no fragments, no surprises. In scientific terms, it is an anomaly fully explained by context. In human terms, it is a reminder of how expectation shapes perception. We look for fireworks, and the universe offers chemistry. What remains is not mystery but precision, a quiet object obeying the same rules as everything else, only longer exposed and harder to read. By the second week of November, 3i Atlas had cleared the sun's glare. Ground-based observatories could track it again, and the results were consistent across every site. The light had dimmed, but its color stayed the same. Blue, steady, gas-dominated. No sign of dust appeared, not even as faint reflection. Telescopes at Mauna Kea in Hawaii, Cerro Paranal in Chile, and the Canary Islands off the coast of Africa measured the decline. Brightness dropped by roughly half each day, a normal rate once solar heating decreased. But the emission spectrum remained identical to what had been seen before. Carbon dioxide, water vapor, and hydroxyl. No silicate peaks, no dust scattering, no tail. In a typical comet, the process works in reverse. Dust lingers long after the gas fades, forming a residual tail that drifts slowly away from the sun. Here, the opposite occurred. Gas activity outlasted everything else, making 3I Atlas look less like a dusty comet and more like a venting asteroid. Active, but sterile. Swift's ultraviolet telescope confirmed continued hydroxyl emission, the signature of water vapor still escaping, though at a lower rate. The gas output dropped sharply but did not stop, suggesting a controlled venting phase rather than an explosive one. The nucleus remained intact, the outgassing steady, a gradual decline instead of collapse. Measurements of how light scattered off the comet supported the same picture. The glow retained a specific pattern, the hallmark of gas-dominated reflection. When sunlight hits solid dust, the scattered light becomes organized in a particular way. Gas molecules scatter randomly, producing a uniform signal. That reading meant the glow was still mostly molecular, not particulate. In physical terms, sunlight was bouncing off mist rather than grains. A faint, diffused halo surrounded the nucleus, but lacked the texture that dust would create. It was color without sparkle. James Webb caught a final observation window in early November and confirmed that the carbon dioxide signature remained strong. Waterlines were weaker but still measurable. Again, no silicate feature appeared at the wavelengths where rocky dust should be. Every instrument repeated the same story. Molecules, no minerals. Comparisons with 2I Borisov provided perspective. Borisov's gas-to-dust ratio was about 1:1, roughly equal amounts of vapor and solid particles. Atlas showed something closer to 9:1 in favor of gas. The difference implied very different birth environments. Borisov likely formed in a region with abundant solid material, close to its parent star, while Atlas probably condensed farther out, where dust never had a chance to coalesce. That fit the chemistry: high carbon dioxide, high water, and low silicate content, a clear cold origin signature. Each observation narrowed uncertainty. By combining infrared, ultraviolet, and visual data, researchers built a thermal model of the nucleus. It showed that after perihelion, the comet cooled faster than expected for a body of its size, another sign of a dense, radiation-hardened shell. That crust, while preventing dust release, also helped it survive. Most comets lose mass rapidly, or fragment near the Sun. 3I Atlas stayed intact. By November 7th, its brightness had fallen to around magnitude 11, too faint for small telescopes. Professional observatories could still track it, but only as a small uniform point. No fragments were detected, no secondary bodies, no debris trail. The nucleus moved outward along a stable trajectory. Intact, silent, fading. At this stage, the data were unambiguous, gas emission only, dominated by carbon dioxide and water vapor. No measurable dust, stable brightness decay, intact nucleus. The evidence supported the idea of a body that had lost its ability to form a tail long before entering our system. It was not a mystery in motion. It was the continuation of a process already finished eons ago. That conclusion did not end the public debate. While the instruments settled into quiet measurement, social media turned the silence into speculation. Posts claimed hidden fragments, filtered images, undisclosed data. The absence of updates felt like proof of concealment to those waiting for drama. In reality, the story had already plateaued. The comet was simply behaving predictably. NASA repeated its earlier statement: data under calibration to be released after verification. ESA echoed it. Routine language, poor optics. When information slows, assumptions fill the space it leaves. Several amateur astronomers reported missing frames from online databases, not realizing that automatic systems remove overexposed or corrupted images as part of standard data cleaning. Procedural maintenance became rumor. It was a reminder that science loses trust, not through secrecy, but through silence that looks like secrecy. For researchers, the focus shifted to understanding broader implications. If interstellar objects like Atlas are shaped by radiation to this extent, how many others pass through unseen because they never produce a visible tail? The detection methods we use, brightness surveys triggered by dust reflection, might be missing entire categories of clean, gas-only bodies. The question moved from why no tail to how many have none. Statistically, interstellar visitors are rare, but with current instruments, rare may simply mean invisible until close. Gas emissions are faint, often lost in background light. 3I Atlas may have been detected only because its flare coincided with the right geometry near the Sun. That realization gave the event long-term value. It was less about anomaly and more about calibration, an opportunity to refine how we search for bodies that look empty. By the end of the week, consensus was complete. Every major dataset agreed. No dust detected after perihelion. Strong gas activity gradually declining. Object intact and leaving the inner solar system. NASA's summary was concise. Observations confirm gas-dominated activity. Nuclear stability maintained. Composition consistent with carbon dioxide and water ices. No speculation. No narrative. Just closure built from data. Outside the research community, the story faded. Headlines moved on and public interest cooled. Inside observatories, the tone was calm. They had watched a body cross the Sun and stay whole. Not a miracle, just a data point that expanded what normal can look like. A comet without a tail is not an exception. It is variation, not error. This time gas won over dust. Next time, the balance may shift again. Each case refines the model. As 3I Atlas receded into the dark, what it left was not spectacle, but clarity. A small piece of interstellar matter passed through our neighborhood, followed every rule of physics, and still looked alien. It did not contradict science. It clarified it. That is what makes it important. By early November, the measurements had stabilized, but the conversation had not. As the data grew clearer, public discussion grew louder. News headlines did not describe the evidence. They framed restraint as mystery. NASA puzzled by tailless comet. Interstellar visitor breaks the rules of physics. Both drew attention. Neither was true. The object behaved consistently. The conversation did not. NASA's official statement was cautious. Activity consistent with volatile-rich cometary behavior. ESA issued almost identical wording. For scientists, that meant agreement. For audiences, it sounded rehearsed. The result was predictable, clarity mistaken for concealment. The agency's communication process explained part of it. Data passed through internal checks before release. That delay protects accuracy, but sacrifices immediacy. In the hours when nothing new appears, speculation fills the gap. It is not conspiracy, it is timing. Independent teams tried to shorten that gap. Observatories in Spain, Chile, and Taiwan posted their measurements directly online. Their numbers confirmed the agency's results. Fading brightness, blue spectrum, gas dominance. Nothing contradictory, but confirmation seldom travels as fast as doubt. Once the phrase "comet without a tail" reached social media, it became a story about secrecy instead of science. Rumors spread. Claims of hidden fragments, missing images, and filtered signals circulated online. None survived basic scrutiny, but each denial generated new theories. The loop was self-sustaining. Silence looked like avoidance. Explanation sounded defensive. Language built for precision struggled in a world built for speed. Avi Loeb addressed the issue directly on November 6th. Open data prevents conspiracies. Delay creates them. He was not accusing anyone. He was describing the pattern, and the pattern repeated itself. Inside research groups, the tone was different. Scientists read the same threads that accused them of hiding results, often during night shifts at observatories. To them, the claims felt surreal. Every number they produced was public, yet the absence of spectacle turned transparency into suspicion. Most stopped replying. A few answered with links to raw data. Neither changed the narrative. This was where sociology met astrophysics. A missing dust tail became a symbol of missing truth. Every technical term, calibration delay, and data validation was recast as code for censorship. Routine process became plot device. Releasing raw imagery was not simple either. Satellite images include cosmic ray streaks and internal reflections that look to untrained eyes like unknown objects. Publishing those frames without context would only amplify confusion, so NASA waited until calibration was complete. Reasonable in method, disastrous in perception. Citizen astronomers filled the gap with their own recordings. Several uploaded sequences showing the same thing, an elongated gas glow with no dust. The redundancy should have ended debate, but emotion outlasted evidence. Once narrative takes hold, facts must compete with entertainment. For the researchers, the event had already moved into the analytical phase. Refined gas ratios showed roughly 3 parts water vapor to 2 parts carbon dioxide. Temperatures near perihelion averaged around 700 Kelvin, hot enough to melt lead, yet the nucleus endured. That resilience impressed scientists far more than any rumor could. Still, the background noise mattered. It showed how fragile public trust becomes when communication lags behind discovery. Skepticism, in moderation, strengthens science. Distrust drowns it. The line between the two is drawn not by data, but by patience. By November 7th, all verified datasets converged. No dust, strong gas lines, intact nucleus. Every instrument agreed. For physics, that was closure. For culture, it was unsatisfying. Many viewers kept waiting for a revelation the data had already delivered. Inside labs, the reaction was understated. No celebration, just relief that results aligned. Some joked that 3i Atlas had become a case study in communication failure rather than comet behavior. Others stopped reading comment threads altogether. The best answer to noise was work. In the end, the lesson was less about astronomy than about process. Science measures slowly. Attention moves fast. When those speeds collide, even ordinary findings become controversial. The comet did not challenge physics. It exposed how information travels. I, Atlas, passed the sun, obeyed every law we know, and left behind a record that anyone can read. The confusion that followed was not born from secrecy. It was born from the human need for drama in a world that mostly runs on data. Every discovery changes its context. 3i Atlas is not just an isolated case. It is a data point in a growing map of interstellar debris. And when compared to its predecessors, patterns start to appear even if they do not align neatly. Oumuamua in 2017 passed silently. It reflected sunlight but released no gas, no glow, no tail. It behaved like rock, not ice. 2i Borisov in 2019 was the opposite, bright, dusty, volatile, and unstable. It looked like a comet from our own solar system, familiar and expected. 3i Atlas now sits between them, active but dustless. 3 objects, 3 chemistries, none fit our categories. The link is not in composition. It is in difference. Each interstellar visitor has rewritten one rule about how comets should behave. Together they outline a continuum from inert to volatile, from dust-heavy to dust-free. That diversity suggests we are not seeing exceptions, but samples from a broader distribution of materials across the galaxy. Every solar system forms in a slightly different chemical environment. Some regions produce rocky bodies, others gas-rich ices. When fragments are ejected by gravitational encounters, they become interstellar travelers like Atlas. By the time they reach us, cosmic rays and micrometeoroid impacts have altered their surfaces beyond recognition. What we see is not origin, it is evolution. The data confirm that interstellar space is not empty. It is a medium filled with radiation, dust grains, and magnetic fields that slowly modify anything crossing it. Atlas carries that record on its crust, a surface changed by billions of years of exposure. In that sense, the comet functions as a sample of space itself, not just of another system. When the first analysis of Atlas began, researchers expected to find primordial matter, a window into another star's disk. Instead, they found a fossil of interstellar travel, a surface cooked by time, chemistry still active but altered. It changed the question from what was it born from to what has it become. Statistically, interstellar visitors should be frequent. Models predict several passing through the inner solar system each year, most too faint to detect. But our surveys rely on visible light reflected by dust. Objects like Atlas, low in reflectivity and poor in particulate matter, slip past unnoticed. We are likely seeing only a fraction of what is really out there. If our detection bias favors brightness, then the dark, clean travelers outnumber the flashy ones. What we call rare may simply be invisible. That realization changes the purpose of these observations. Each interstellar body we track is not just an anomaly, but a calibration tool. It shows us which kinds of matter our instruments ignore. In that light, 3i Atlas is useful precisely because it looked strange. It forced telescopes to record spectra instead of color, gas instead of glow. It reminded researchers that absence is a form of information. No dust means a specific chemistry, a precise history, a definable path. At its core, the case of Atlas is about adaptation, both cosmic and human. The comet adapted to radiation. Science adapts to uncertainty. Each step in the observation required letting go of assumptions built from local examples. The lesson was not about alien behavior, it was about context. By mid-November, papers were already in preparation. Titles varied: Gas-dominated interstellar comet, Dust suppression in 3i Atlas, Surface processing by cosmic rays. Different angles, same data. No sensationalism, just incremental understanding. Patterns like this accumulate slowly. One comet alters expectations, the next refines them. In a decade, the category of interstellar object may include dozens, each with its own spectrum and density. When that happens, anomalies will dissolve into statistics. Atlas did not break physics. It stretched our sample size. It showed how objects from beyond our system obey the same thermodynamics and the same chemistry, only shaped by longer exposure and colder origins. It is an outlier only because we have just started counting, and that is the broader view. 3 travelers, 1 framework, expanding quietly as data replace surprise. Each object crosses our path once. Each one leaves a single line in the record, short, factual, and irreversible. When the noise faded, the work stayed. The kind of work that does not trend or tweet, just the slow, patient building of understanding. Picture it. Hundreds of researchers comparing spectra, light split into colors to reveal what it is made of, cleaning noise 1 pixel at a time. No drama, only precision. Each dataset spoke the same truth in a different accent. Soho gave brightness, stereo gave geometry, Swift gave chemistry, Webb gave depth. Together they formed one image, a gas-rich interstellar comet that survived its closest approach to the Sun without breaking apart. Simple words, big implications. At Lulin Observatory, Zhang's team refined their brightness measurements. Their report read quietly, post-perihelion activity remains stable. No particulate emission detected. In plain English, the comet kept venting gas but no solid grains escaped, still breathing without shedding skin. At the US Naval Research Lab, Batam's group checked raw satellite frames for artifacts. They found none. No hidden tail, no imaging glitch. The absence repeated. In science, that is the definition of certainty, when every correction leaves the pattern intact. The next step was modeling. Teams ran thermal simulations, digital experiments showing how ice turns straight into gas without melting first. They adjusted parameters such as crust thickness, rotation speed, and solar heating. If the model matched the real observations, the mystery shrank into mechanics. One early simulation worked almost too well. A 10-centimeter carbon dioxide crust could delay water release until heat cracked it open, causing the 40-fold gas spike observed near the Sun. Then the crust resealed. No magic, just timing. Each explanation lowered the drama but raised the accuracy. At the Royal Belgian Institute, Maggiolo's team merged radiation chemistry into those models. Radiation chemistry, the study of how cosmic rays change ice over long timescales, predicts that surfaces exposed for billions of years lose dust-producing material. 3i Atlas fit the curve perfectly. That made the missing tail not an anomaly, but a forecast fulfilled. Think about that inversion. Surprise turning into expectation. NASA's interim note on November 7th read, "Gas-dominated activity confirmed, structural integrity maintained, composition consistent with carbon dioxide and water ices." No adjectives, no spin, just the essential line. No significant dust component detected. The European Space Agency repeated the statement within hours, not as choreography, but as consensus. In science, echo means alignment. That is the sound of understanding landing quietly. Cross-calibration came next. Webb's infrared data were compared with Swift's ultraviolet flux. Both measured temperature independently, and results agreed within 5%, about 700 Kelvin at perihelion, cooling to 450 Kelvin days later. Hot enough to melt metal on the surface, cold enough for ice to hide underneath. That is thermal inertia, the tendency of large bodies to change temperature slowly. It explains how a surface can flare while the core stays frozen. Independent labs pushed further. They built comet analogues, frozen mixtures of carbon dioxide, ammonia, and silicate dust, chilled to -220 degrees Celsius. Then they bombarded them with protons to mimic cosmic rays. The samples darkened, hardened, vented gas bursts under heat, but produced almost no dust. Exactly what Atlas did in space. Replication beats speculation. Look at that, a one-to-one match between lab and sky. That is when anomaly becomes dataset. Yet curiosity did not stop. How many earlier comets acted this way without anyone noticing? Gas tails are faint and easily lost in glare. Maybe 3i Atlas is not rare, only finally seen clearly. Think about that shift. The extraordinary shrinking into ordinary physics. Still beautiful, just better understood. NASA's full archive for satellite observations opened the same day. Thousands of unfiltered frames, each showing the same blue filament, the same clean coma, the same silence of dust. Transparency won slowly, but it won. The thing people suspected was hidden turned out to be the only thing visible to everyone. Gas, light, data. There was neither conspiracy nor miracle, only record. By the end of the week, the story was complete. The comet moved on. The science settled. That is what real discovery sounds like when the microphones are off. By mid-November, the data stopped moving. Brightness down, spectrum steady. Follow-up readings from the European Southern Observatory matched what Swift saw days earlier. 3 instruments, 3 teams, same results. When independent tools converge, doubt fades quickly. That is how science builds confidence, by repetition, not volume. Zhang summarized it in one line. Behavior consistent with cometary physics, but with an unfamiliar balance. It sounds cautious, but that sentence quietly rewrote expectations. The laws of physics held. Our assumptions did not. Every claim of hidden dust collapsed under calibration. Imaging errors were ruled out. What remained was absence, proven, measured, repeatable. No dust tail in any wavelength from visible to infrared. Thermal models closed next. Gas dynamics, solar wind pressure, and sublimation curves all led to the same image. A compact nucleus, an irradiated crust, a burst of volatile gas, and a clean exit. Volatiles, the ices that evaporate quickly when heated, drove everything. No exotic forces, just ordinary chemistry seen up close for the first time. After weeks of noise, the mystery dissolved into mechanics. It did not vanish. It clarified. Most of our comet models are local, built from solar system examples. They assume one sun, one kind of dust, one chemistry. 3i Atlas did not come from here. Its materials formed under another spectrum, colder, poorer in silicates, richer in carbon. Different conditions, same physics. Researchers went back through archives and found faint precursors. Comets once marked as unusual, now understood as dust poor. We had not lacked evidence, only context. Sometimes anomalies are just forgotten categories waiting to be recognized. NASA's internal essay on November 7th captured that humility. 3i Atlas reminds us that the absence of evidence can itself be evidence of precision. To measure nothing and be certain of it is a kind of success. Inside observatories, relief replaced excitement. After weeks of speculation, the data aligned cleanly. They had watched a comet challenge their models without breaking their laws. The universe had not changed. Understanding had caught up. By the time the reports closed, the record was complete. The visual magnitude had faded near 11. The blue continuum came from gas fluorescence. The nucleus remained stable with no dust plume, and the gas composition showed CO2, H2O, and faint traces of NH2 and C2. No artificial signals, no fragments, nothing unexpected. That was all it was, and that was enough. An interstellar traveler had passed the sun, leaving behind a curve of data so precise it silenced argument. Yet one lesson stayed with the scientists. The problem was never physics. It was communication. A faster release of data might have stopped the noise. Simpler words might have built trust. But truth never travels as fast as rumor. Our atlas didn't test the laws of motion. It tested our patience. It reminded us that sometimes silence, measured carefully, becomes the loudest discovery of all. When the numbers finally steadied, what remained wasn't just data. It was perspective. Every frame and every line of spectra felt less like a mystery and more like a mirror. The comet hadn't broken any rule of nature. It had only shown how quickly we invent stories when faced with silence. A comet lost its tail, and the world filled the void with meaning. NASA's debrief put it plainly. Scientific behavior remained within normal parameters. Public reaction did not. It wasn't criticism, just observation. The physics behaved. People didn't. We wanted revelation, not routine. But science rarely moves through shocks. It moves through clarity. And 3i Atlas forced that clarity on everyone watching. Think of it. A fragment older than Earth, crossing our solar system, warmed by our sun for the first and only time before continuing on its way. We measured its chemistry, tracked its light, and called it an anomaly only because it stayed ordinary. And that says more about us than about it. Zhang later wrote, "We measured absence as presence." Batams called it a case study in restraint. Both meant the same thing. Confirmation can be more powerful than discovery. Science lives in that patience, in the act of watching without demanding drama. But patience doesn't trend, and speculation filled the air until the truth sounded almost dull. Still, there's a quiet poetry in that dullness. Interstellar objects don't arrive for us. We simply intersect their paths for a moment and then lose them again. They don't send signals. They just exist. Our curiosity does the rest. For centuries, comets were omens. Then they became equations. Now they stand somewhere in between. Still mythic in attention, but purely physical in nature. Each new measurement strips away a little superstition and replaces it with understanding. That's what progress feels like. Less fear, more patience. Imagine standing under a November sky, knowing that one of those faint points once came from another star. It carries traces of radiation, layers of dustless ice, and scars from cosmic rays. And now it reflects sunlight from our own star. Our photons travel with it into the dark. Observation becomes reciprocity. We send light, and we receive knowledge. Atlas joins a short list. Oumuamua, the silent rock. Borisov, the dust storm. And Atlas, the clear breath. 3 different chemistries, 3 different temperaments, one shared message. The universe creates more variety than imagination ever could. NASA's final statement didn't reach for metaphor. Observations complete. Data consistent with cometary activity. Simple and sufficient. Yet between those lines was something human. Relief, curiosity, maybe a trace of awe. Because truth is quiet. It never shouts. It waits for us to listen through the noise. What 3i Atlas proved wasn't that something extraordinary had happened. It was that the ordinary, seen closely enough, can still stop us. A comet without a tail, moving faster than any probe we've built, carrying chemistry older than our sun. That's extraordinary enough. Maybe that's the real discovery. Endurance is measurable. Every observation confirmed it. The comet endured radiation, distance, and scrutiny. And so did the idea of truth itself. Now it's gone. Too dim for any telescope. The story returns to silence. But every photon it reflected remains archived. A trace of light from another system crossing ours. We didn't catch a mystery. We caught motion. And for a brief moment, that was enough. By the time 3I Atlas slipped beyond the reach of observatories, its story was already complete. It left no tail and no fragments, only a faint trace of blue light fading into the dark. Telescopes in Chile, Hawaii, and the Canary Islands caught the last glints, faint dots barely above the noise floor, magnitude around 11 and falling, still gas-rich and dustless, still following the same clean physics that had caused so much noise only weeks earlier. Imagine standing outside on one of those nights, knowing that a traveler from another star is moving away, too faint to see, but still real. That feeling, not discovery but awareness, is the quiet part of science we rarely talk about. All the data now sit in archives, satellite coronagraphs, ultraviolet spectra, infrared curves. Every record confirms the same pattern. Gas-driven activity, CO2 and water emission, no silicate dust. Volatiles, the ices that evaporate under heat, drove all visible behavior. Nothing exotic, nothing hidden, nothing withheld. That's the kind of certainty scientists work for. Convergence, not drama. NASA's summary on November 7th ended the analysis clearly. Object intact, activity declining, composition consistent with volatile-rich comet. One short line that took months of measurement to earn. The European Space Agency echoed the same, word for word. Consensus doesn't sound exciting, but that's what progress looks like. And here's the larger view. 3I Atlas is no longer an anomaly, it's a precedent. The first clear case of a dustless interstellar comet, documented from start to finish. That changes how models of comet evolution work, how we think radiation, chemistry, and distance interact over time. If exposure to cosmic rays can turn ice into armor, then countless other travelers may have passed unseen, invisible to telescopes tuned for dust. What we once called rare might simply be what we never noticed. The galaxy constantly trades material between stars. Some fragments burn in new suns while others drift for ages. We're only now learning how to find them. Our solar system isn't sealed. It breathes, exchanging matter with the rest of the galaxy. 3I Atlas is proof of that quiet circulation. In a way, it's humbling. The object wasn't performing. It was simply passing through, and we just happened to look up at the right moment. Now all the files are public. Thousands of images open to anyone willing to explore them. Students, researchers, and amateur astronomers can trace the faint signature for themselves. That's what real transparency looks like when it works. Curiosity rewarded and speculation starved. Soon there will be another interstellar detection, with a different angle and a different chemistry, but this one leaves a clear template behind. Measure, release, compare, repeat. That rhythm is what keeps science alive. The story ends just as it began, quietly, without revelations or cosmic secrets, only with the slow fading of reflected light. Yet the silence it leaves behind isn't empty, it's full of context. A comet without a tail crossed our sun and reminded us what patience really looks like. That's all, and that's enough. Because in the end, astronomy isn't about spectacle, it's about watching long enough for truth to settle. The light fades, the data remain, and the sky resets, open, calm, waiting. The instruments have moved on, and the data streams are archived, yet that faint blue trace of 3I Atlas still lingers, a quiet line of light crossing memory more than sky. What began as a simple detection ended as understanding. A traveler from another system passed close to our sun, released gas, kept its shape, and continued on its way. No tail, no fragments, no mystery beyond patience. Everything that could be measured was measured. Everything else became silence. Imagine it for a moment. An object older than our planet, and even older than our sun, reflecting our light, once before vanishing again into the interstellar dark. That reflection remains, stored in images, in spectra, in code. Data are the only way to hold something that will never return. Atlas didn't change physics, it confirmed it. It showed that the laws we know reach as far as the visitors We don't. That's the kind of reassurance only the cosmos can offer. NASA's final note closed with one simple line: observation complete. Object outbound, plain words, but behind them a quiet respect for what passed through and for the act of watching itself. The story doesn't really end here. It simply leaves the frame, because out there beyond every telescope, 3i Atlas is still moving.